Hello and welcome! Today we are putting on our detective hats and diving into a mathematical mystery. We're on the case of a really common but super powerful type of clue, the first-order linear differential equation. Now, I know that sounds like a mouthful, but trust me, by the end of this, you'll see it's just a cool puzzle with a seriously elegant solution. So think about it like this. How do you find something when you don't know where it is, but you have perfect information about how it's moving or changing at any given moment? That's really the heart of the problem we're tackling today. We've got an equation that describes a function's rate of change, and our job is to use those clues to work backward and find the original function itself. All right, let's set the scene. Our culprit, the thing we're trying to track down, is an unknown function that we'll just call y. And all the clues we have to go on, they're all wrapped up inside this one thing called a differential equation. And this right here is our main piece of evidence. This equation is telling us a story. It says that the way our function y is changing, that's the dy over dx part, is connected to the function y itself, along with a couple of other functions, p of x and q of x. You can think of p and q as the known accomplices in this whole mystery. You know, any good detective will tell you that the very first step is to organize your clues. And in math, it's no different. We need to get our equation into what we call standard form. It's all about arranging the evidence in a very specific way, because that's how you start to spot the hidden patterns. And this is it, the official standard form. When an equation fits this exact structure, we know we're dealing with a first-order linear differential equation. And that word linear is super important. It just means you're not going to see any weird stuff like y squared or the sine of y. Our function y and its rate of change are just there as they are. This specific structure, well, it's the key that's going to unlock this entire case. But here's our first plot twist. If you just look at that left-hand side, that dy by dx plus p of xy, and you try to integrate it as is, well, you can't. It's just a messy jumble of terms that doesn't fit any of the normal integration rules. Honestly, it feels like we've hit a total dead end. So what happens when a detective hits a wall? They don't just give up. They pull out a special tool. And for us, that tool is a kind of mathematical secret weapon. It's like a decoder key, and it's called the integrating factor. Its entire job is to take this messy, unsolvable equation and transform it into something surprisingly simple. So here's the big idea, the master plan. We are going to multiply our entire equation by a very cleverly chosen function. Let's call it I of x. And we're not just doing this for fun. It's a strategic move designed to make the left-hand side of our equation morph into something that we actually recognize from calculus, something we can solve. Okay, and this is the aha moment right here. On the left is what we have after we multiply by our secret weapon, I, and on the right, that's just the product rule for derivatives. You know, the derivative of I times y. Now, look really closely. They are almost identical. The only difference is that I p of x on the left versus the I prime on the right. So what if we could choose our function I so that its derivative I prime was exactly equal to I times p of x? Then the two sides would be a perfect match. And here it is. This is the identity of our secret weapon. The function that perfectly satisfies the condition we just dreamed up is e raised to the power of the integral of p of x. This is our integrating factor. Yeah, it might look a little intense, but it is purpose-built to crack this exact kind of code. All right, we've got our secret weapon. Now it's time to blow this case wide open. This is where all that setup starts to pay off, and you're going to see this mystery just completely unravel. Would you look at that? After we multiply by our special I of x, that messy, complicated left side has completely collapsed into something simple, just the derivative of I times y. And the right side is now just I times q. The path forward is suddenly crystal clear. All we have to do is integrate both sides, and we can finally free our unknown function y.
So let's just write down our detective's handbook here. It's a straightforward four-step method. Step 1, get your clues in order, put the equation in standard form. Step 2, find your secret weapon. Calculate that integrating factor I. Step 3, multiply everything by I, which then magically simplifies that left side. And finally, step 4, integrate both sides to solve the mystery and find y. That's it.
Okay, theory is one thing, but let's see how this method actually works on a real case. We're going to pull a problem from the files and walk through it step by step, putting our four-step method to the test. And here is our case. Now, right off the bat, you can see it doesn't quite look like our standard form, right? That y prime term, which is just another way to write dy dx, it's got that x squared plus 1 hanging around. So our first step should be pretty obvious.
So for step 1, we just divide the whole equation by x squared plus 1 to get that y prime by itself. And just like that, it's in perfect standard form. Now we can clearly see that our p of x is the 3x divided by x squared plus 1 bit, and our q of x is 6x divided by x squared plus 1.
Now for step 2. We take our p of x and we plug it into our secret weapon formula, e raised to the integral of p of x. Now, solving this integral takes a little bit of calculus, a u substitution. But once you turn the crank, you find that the integrating factor for this specific case is x squared plus 1 raised to the 3/2 power. And now for the magic. We move on to step 3, multiplying our equation by this integrating factor. And, just as we designed it to do, the left-hand side beautifully collapses into the derivative of our integrating factor times y. This sets us up perfectly for step 4, where we just integrate both sides, and that is what will finally get us our answer for y.
And there it is. The identity of our mystery function is revealed. We have successfully unmasked y. And that c you see there, that's just our constant of integration. It means there's a whole family of functions that work, but we've cracked the fundamental structure. Case closed.
You know, the integrating factor is an absolutely brilliant tool, but it was custom built to solve this one very specific type of problem. It really makes you wonder, doesn't it? For every single type of mathematical mystery out there, what other amazing secret weapons and clever tricks are just waiting for someone to discover them? Thanks for cracking this case with me today.